Hi guys, this video is about a summary of the patterns in the periodic tables. So first, I'm going to summarize the terms that we learned in this topic. So we have effective nuclear charge, all right, and also known as core charge. Now, what is that effective nuclear charge? Effective nuclear charge is the attraction force of the protons from the nucleus towards the electrons in an atom. Okay, so basically the electron will experience the attraction force from the positively charged protons, and that's what we call effective nuclear charge. So the higher the number of protons, the stronger the attractions of the protons towards the electrons. So it's more tightly held to the nucleus. Okay, now what is that core charge then? Core charge is in a mathematical way that we can calculate, and it can be shown in the number how strong is the effective nuclear charge. Now let's take as an example, let's say sodium. So I should have 11 protons in sodium and of course 11 electrons. Okay, they should be the same because sodium atom is a neutral atom. So in this case, the electron configurations for sodium is 2.8.1. All right. So how to calculate core charge? How do I know what is the effective nuclear charge? So we use the proton number, which is 11. And remember that even though sodium changed into an ions, okay, proton number remain unchanged. So I have 11 protons. I'm going to minus the internal electrons. Now everybody know this one single electron is so-called the valence electrons. All right. So whatever electrons out of the valence shell, we call that as the internal electrons. And these internal electrons, I'm going to put it here. So total I have 10. So 11 minus 10. Proton number minus internal electrons, you get positive 1. And that's the nuclear charge, also called the core charge of sodium. All right, so this is the core charge of sodium. Now, what if I use magnesium as an example? So I have 12 protons and 12 electrons. So what is the configurations? 2.8.2. All right, and what is the core charge? I'm using 12, which is the proton number, minus the internal electrons, which is 10. Then I will get a positive 2 core charge. So in this case, the core charge of magnesium is higher than sodium, which means the electrons in magnesium is strongly held by the nucleus as compared to sodium. So magnesium has a higher effective nuclear charge than sodium. All right, that's effective nuclear charge. Now, then we talk about the trend in the periodic table. So what is the trend for effective nuclear charge in the periodic tables? Now, when you move across a period, okay, when you move across a period from left to right, nuclear charge or core charge increases. Okay, when you move across a period, proton number increase, core charge increase. All right, so that's across a period. Now, what about down the group? So when going down a group, for example, going down group 1, what happened is the electron shells will be increasing from period 1, period 2, period 3, 4, 5, 6. When the number of period increases, the electron shell increase. So when going down a group, core charge, if you calculate it, should remain the same. Okay, so this is the trend for core charge or effective nuclear charge. All right, so next, we're going to look at another term. We call it as shielding effect. Sometimes they call it as screening effect, right? It doesn't matter, it's just a different terms, the same explanation. All right, what is that shielding effects? For example, I have sodium again. So configuration is 281, all right? And then I have the potassium within the same group. I have 2.8.8.1, 19. All right, so let's try what is shielding effect. Now, shielding effect is the repulsion force between the internal electrons. Now, I explained just now what is internal electrons. Other than valence shells, other than the electrons in the valence shells, whatever electrons are known as internal electrons. Now, what is the internal electrons in sodium? I have 10. Okay. What is the number of internal electrons in potassium? This is valence. So other than valence, I have 18 electrons. So which one do you think exerts a greater repulsion force between electrons? I have 10 and 18. Of course, 18. This one should have greater repulsions. And why is that a repulsions? Because electrons are negatively charged, and you put them together, whether you have a distance between them or you put them into the same shells, they still gives a repulsions. Okay, they still give a repulsion. So when you have more electrons, it will definitely give you a greater repulsions. Okay, now what happened to this shooting effect when repulsion increase? When repulsion increase, shooting effect increase, and it will shield the valence electrons away from the nucleus, which means indirectly, when shooting effect increase, the size of an atom will increase. Okay, the size of an atom will increase. It's like it expands. Okay, it expanding. It expands to a bigger size or bigger radius when greater repulsions from the internal electrons. All right, now that's shooting effect. Next, we could talk about the trend in the periodic table for shooting effect. Now, what happened when you move across a period in terms of shooting effect? So shooting effect, when you move across a period, it stays relatively constant. All right, across a period, it stays relatively constant. And what happened when going down the group? Shielding effect increases. Now, why is it increases? Because when going down the group, you have additional electron shells. So the more electron shells you have, the more internal electrons you have, and therefore greater internal repulsions, hence shooting effect increase. All right, and when you move across a period, why the shooting effect stayed relatively constant? Because when you move across a period, the number of electron shells remain the same. All right, and why is it relatively constant? Relatively constant means it is not 100% constant. All right, it's not 100% constant. Why is it not 100% constant? Because when you move across a period, you have additional electrons. Okay, even though the electron shell number remain the same, but you keep adding additional electrons to the valence shells, and these additional electrons will still give a certain extent of repulsions, but this repulsion is smaller than the repulsions between electron shells. It still gives you repulsions, but it's not as significant as the one between electron shells. All right, so it stays relatively constant, which means it will still have repulsions when you have additional electrons. It just increased slightly. All right, compared to when you have additional electron shells. Okay, so these are the trend for shooting effect in the periodic table. All right, so next, move on. The three properties that we need to know in the periodic table. So namely, number one, we have atomic radius. All right, number two, we have ionization energy. Number three, we have electronegativity. Okay, let's explain one by one. So atomic radius is obviously the size of an atom. How big is that? All right. Ionization energy is the energy required to remove an electrons from an atom or an ions. As long as you remove electrons from it, you need energy to do that. You need energy to overcome the attractions of the protons and electrons. So therefore, they call it as ionization energy, and it's always positive endothermic. I hope you still remember what is endothermic. All right. Electronegativity is the tendency of an element to accept an electron. Okay. The higher the electronegativity, the easier for it to become a negative ions. So that's electronegativity. All right. Now, how these three change in a periodic table and why are they changing? All right. So first, we look at atomic radius. So when you move across a period, what happened to the atomic radius when you move across a period? Okay, let me change a bit on this. Move it aside. I draw you a table. So across a period. So what happened when you move across a period in terms of atomic radius? Atomic radius decreases. Okay, it shrinks in size. Ionization energy actually increases. Electronegativity increases. All right, this is across a period. And what about down a group? So atomic radius increases. Ionization energy decreases. Electronegativity decreases. Okay, now if you notice that they're actually opposite to each other. Across a period, decrease for atomic radius, but increase in terms of going down the group. So same goes to ionization energy and electronegativity. Now, what makes them decrease and increase across a period and down the group? So this trend is actually mainly affected by the two terms that we have discussed just now, core charge and shielding effect. Okay, so that is the general trend. Let me explain more in details on how core charge and shielding effect affects the atomic radius, ionization energy, and electronegativity. Now we have core charge here. Sorry. Okay, so when core charge increases, what happened to the atomic radius? Okay, and what happened to ionization energy? What happened to electronegativity? Okay, so in terms of atomic radius, when core charge increases, atomic radius will actually decrease because stronger attractions from the protons, from the nucleus, it pulls all the electrons towards the nucleus. So it makes the size shrink, all right? It makes it smaller. And what happened to the ionization energy when core charge increase? Of course, ionization energy will increase. So when core charge increase means stronger attractions. So more energy actually required for you to remove the electrons from an atom or an ions. Okay? Electronegativity. What happened? When core charge increases, electronegativity, the tendency to attract or to accept an electrons will increase. The same reason, stronger core charge, stronger attraction force, the tendency to pull extra electrons into the atom is higher. Okay, so this how core charge affects atomic radius, ionization energy, and electronegativity. Next, we look at shielding effect. Now, how shielding effect actually affects the three properties here. We have atomic radius, electronegativity, and ionization energy. Let's look at shielding effect. Okay, so shielding effect. Now, when shielding effect increases, what is the effect on atomic radius? So when shielding effect increase means more internal electrons, greater repulsions, the valence electrons will be shielded away from the nucleus, further away from the nucleus. And that's the reason why atomic radius increases. Okay, it increases the atomic radius. And when shielding effect increases, what happened to the ionization energy? Like I said, the valence electron is actually further away from the nucleus, weaker attractions. And that's the reason why the ionization energy needed to remove it will be easier. So ionization energy will decrease. All right. Electronegativity, tendency to accept or to attract electrons. So when shielding effect increase, weaker attraction because it's further away from the nucleus. Therefore, electronegativity decreases as well. Okay. Now this is how shielding effects affects the three properties in terms of the periodic table. Okay, I just explained one side of it, like core charge increase, shielding effect increase, right? So what if core charge decrease and shielding effect decrease? Of course, the trend will be the other way around. Everything's opposite. Okay, now last one, I'm going to explain something very tricky here. Now, what if you have an element or an atom, element X, for example. Now, element X compared to element Y. Okay, so the configuration for X will be 2, 8, 1. All right, element X is 2, 8, 1. So element Y is 2, 8, 8, 1. Okay, now if you compare in terms of X and Y, for example, I choose one property, atomic radius. So which one, X or Y, having a higher, a bigger atomic radius? Okay, so how to know whether it's something we have bigger atomic radius? Again, we check the core charge and the shielding effect. So what happened to the core charge of element X? The core charge will be 11 minus 10. The internal electrons, you get positive 1. That's the core charge. And what happened to your Y in terms of core charge? You have 19 minus 18, positive 1. Now the core charge remain the same between X and Y. So next we're going to check shielding effect. Now what is the shielding effect here? The internal electrons. I have how many internal electrons for X? 10 electrons again. And how many electrons for Y? The internal, except the valence, I have 18 electrons. So which one giving you a high shielding effect? Element Y. So in conclusions, Y has higher shielding effect and same core charge as X. All right, Y has high shielding effect but same core charge as X. So which one do you think having a larger radius? Yes, the answer is Y. But why? Because higher shielding effects repel the electrons away from the nucleus. It makes it bigger. At the same time, the core charge is the same as X. The attraction force is the same as X. So one with higher shielding effect but same core charge, of course, the atomic radius will be bigger. Okay, this is just an example explaining in terms of shielding effects and core charge. So hope you're clear about that. And remember this, whenever you have comparing core charge and you're comparing core charge and shielding effect, we always take shielding effect as dominant, core charge only when shielding effect is constant. Okay, so if an element with increasing shielding effect and increasing core charge, for example, shielding effect increase, core charge also increase. So what happened to its ionization energy? What happened to its atomic radius? When an element with increasing shielding effect and increasing core charge, stronger attractions, also greater repulsions, we consider only shielding effect because, as I said, this takes dominant. So when shielding effect increasing, regardless of whether core charge increase or the same, the size or the atomic radius will increase. The ionization energy needed to remove an electrons will be decreasing. Okay, will be decreasing, and the electronegativity when shielding effect increase will be decreasing as well, even though core charge increase. Okay, so remember that when you're comparing both core charge and shielding effects, even though both are changing, shielding effect takes dominant. Unless shielding effect stay constant, then core charge will come into the picture and take effect. Okay, hope this helped after you have gone through the online content. All right, anything you're not sure, feel free to ask during tutorial sessions. All right, see you.